Hello everyone, welcome to my channel. If you are new to my channel, please subscribe to my YouTube channel, so you can join our tech family. If it is informative to you, please like our video, share it with your friends so they can get help with these video, and don't forget to press all notification bell icon so you get regular update and don't miss any single video.
Client-side attacks. Client-side attack vectors are especially insidious as they exploit weaknesses in client software, such as a browser, as opposed to exploiting server software. This often involves some form of user interaction and deception in order for the client software to execute malicious code. These attack vectors are particularly appealing for an attacker because they do not require direct or routable access to the victim's machine. For example, imagine that an employee inside a non-routable internal network has received an email with an attachment or a link to a malicious website. If the employee opens the attachment or clicks on the link, the content, which may be a document or the contents of a web page, is sent as input to a local application on their machine. The application will then render that input and could execute malicious code. The employee's machine would then be exploited, perhaps launching a remote shell from the compromised machine out through the firewall to a listener on the attacker's machine. In this module, we'll describe some of the factors that are important to consider in this type of attack and walk through exploitation scenarios involving both malicious HTML applications and Microsoft Word documents. Know your target. From an attacker's standpoint, the primary difficulty with client-side attacks lies in the enumeration of the victim's client software. The secret to success in client-side attacks is, as with most things related to penetration testing, accurate and thorough information gathering. We can use both passive and active information gathering techniques against our client-side attack targets. Passive client information gathering. When leveraging passive information gathering techniques, we do not directly interact with our intended targets. For example, in a recent engagement, we were tasked with attempting to compromise corporate employees with client-side attacks and various phishing techniques. However, we were not allowed to make phone contact with employees. Given that restriction, we Googled for various known external corporate IP addresses and found one on a site that hosts collected user agent data from various affiliate sites. This information, similar to that in this screenshot, revealed the underlying operating system version of a corporate client machine. It also revealed the browser type and version along with installed plugins as listed in the user agent string. We modified an existing exploit and launched it against one of our lab machines running the same operating system and browser version as our target. The test was a success, so we used the exploit in a client-side attack against our corporate target, and were rewarded with a reverse shell. We can find this type of information fairly often on websites, in IRC logs, and even in photos posted to social media. Time spent doing research is never wasted. Active client information gathering. By contrast, active client information gathering techniques make direct contact with the target machine or its users. This could involve placing a phone call to a user in an attempt to extract useful information, or sending a targeted email to the victim hoping for a click on a link that will enumerate the target's operating system version, browser version, and installed extensions. We'll explore active information gathering techniques in this section. Social engineering and client-side attacks. As most client-side attacks require some form of interaction with the target, such as requiring the target to click on a link, open an email, run an attachment, or open a document, we should preemptively leverage social engineering tactics to improve our chances of success. Imagine the following scenario. We're on an engagement trying to execute a client-side attack against the Human Resources Department. We could just blindly jump in and attack, but our chances of success are slim since we have no idea which operating system and applications they're using, nor which versions. Instead, we'll favor caution and respond to a job posting with a malformed resume document that is designed to not open. The next day, we receive an email response indicating that, not surprisingly, HR cannot open our document. In an attempt to help resolve the issue, we respond, asking what exact version of Microsoft Office they're using, suggesting that the issue may be caused by a version incompatibility. In our scenario, we discover that the HR representative is unsurprisingly using a specific version of Microsoft Office and that they are allowed to execute Word macros. Armed with this information, we can craft a second resume Word document containing a macro leveraging PowerShell to open a reverse shell and email it to them. Of course, this is a simplified success story. Your social engineering pretexts will most certainly have to be more intricate and specific based on information you have gathered in advance. Client fingerprinting. The process of client fingerprinting is extremely critical to the success of our attack. But to obtain the most precise information, we must often gather it from the target machine itself. Let's assume we've convinced our victim to visit our malicious web page in a practical example. Our goal will be to identify the victim's web browser version and gather information about the underlying operating system. We could create our own custom tool, but there are many available open source fingerprinting projects. The most reliable are generally those that directly leverage common client-side components, such as JavaScript. For this example, we'll use the Fingerprint.js2 JavaScript library, which can be installed by downloading and extracting the project archive from its GitHub repository. Let's unzip the fingerprint application, move it to the FP directory, and incorporate this library into an HTML file based on the examples included with the project. We'll include the fingerprint2.js library from within the fingerprint2.html file located in the FP directory of our Kali web server. The JavaScript code invokes the fingerprint2.get static function to start the fingerprinting process. The components variable returned by the library is an array containing all the information extracted from the client. The values stored in the components array are used to create a hash fingerprint of the browser, which is assigned to the murmur variable. Finally, the same values are extracted and displayed in the HTML page. In our Windows client, we'll simulate a victim navigating to the fingerprinting web page. The web page in our Windows Lab machine reveals that these few lines of JavaScript code extracted the Windows browser user agent string, its localization, the installed browser plugins and relative version, generic information regarding the underlying Win32 operating system platform, and other details. Submitting this user agent string to an online user agent database identifies the browser version and operating system as Edge 41, running on the 32-bit version of Windows 10. We managed to gather the information we were after, but the JavaScript code displays data to the victim rather than to the attacker. This is obviously not very useful, so we need to find a way to transfer the extracted information to our attacking web server. We'll create a file that will act as a fingerprinting web page and add a few lines of AJAX code to send the data back to our web server. In this code, the XML HTTP request JavaScript API interacts with the attacking web server via a POST request. The POST request is issued against the same server where the malicious web page is stored. Therefore, the URL used in the XML HTTP.open method does not specify an IP address. The components array, which contains the information extracted by the Fingerprint2 library, is processed by a few lines of JavaScript code, similar to the previous example. This time, however, the resultant output string, the client FP variable, is sent to js.php via a POST request. Let's look at the js.php code that processes the POST request on the attacking server. The PHP code first extracts the client IP address from the $_server array, which contains server and execution environment information. Then the IP address is concatenated to the text string received from the JavaScript POST request, and finally written to the fingerprint.txt file in the FP directory. Notice the use of the file append flag, which allows us to store multiple fingerprints to the same file. In order for this code to work, we need to allow the Apache www data user to write to the FP directory. To do this, we'll change the owner of the FP directory to www data. Once the victim browses the Fingerprint2 server.html web page, we can inspect the contents of fingerprint.txt on our attack server. The XML HTTP request silently transferred the data to our attack server without any interaction from the victim. Leveraging HTML applications. Next, we'll turn our attention to specific client-side attacks, beginning with an attack against HTML applications. HTML applications allow arbitrary execution of applications directly from Internet Explorer, rather than downloading and manually running an executable. If a file is created with the extension of .hta instead of .html, Internet Explorer will automatically interpret it as an HTML application and offer to execute it with the mshta.exe program. Since this clashes with the security boundaries in Internet Explorer, an HTML application is always executed outside of the security context of the browser by the Microsoft signed binary mshta.exe. If the user allows this to happen, an attacker can execute arbitrary code with that user's permissions, avoiding the security restrictions normally imposed by Internet Explorer. While this attack vector only works against Internet Explorer and to some extent Microsoft Edge, it is still useful since many corporations rely on Internet Explorer as their default browser. This vector leverages features directly built into Windows operating systems, and more importantly, it's compatible with less secure Microsoft legacy web technologies such as ActiveX. Exploring HTML applications. Similar to an HTML page, a typical HTML application includes HTML, body, and script tags, followed by JavaScript or VB-script code. However, since the HTML application is executed outside the browser, we're free to use legacy and dangerous features that are often blocked within the browser. In this example, we'll leverage ActiveX objects, which can potentially and dangerously provide access to underlying operating system commands. We can achieve this through WScript, and in particular, the Windows Script Host Shell object. Once we instantiate a Windows Script Host Shell object, we can invoke its run method in order to launch an application on the target client machine. Let's create a simple proof of concept HTML application that launches a command prompt. Our code assigns a variable to a Windows command executable. This variable is then run with ActiveX object and our Windows Script Host Shell object. We can place this code in a file on our Kali machine and serve it from the Apache web server. Once a victim accesses this file using Internet Explorer, they'll be presented with a pop-up dialog. This dialog is the result of an attempted execution of an HTA file. Selecting Open will prompt an additional dialog, since the sandbox protection of Internet Explorer, also called Protected Mode, is enabled by default. The victim can select Allow to permit the action, which will execute the JavaScript code and launch cmd.exe. This is a start, but it's not as clean as it could be. While mshta.exe is executing, it keeps an additional window open behind our command prompt. To avoid this, we can update our proof of concept to close this window with the close object method. Now we can again access our proof of concept in Internet Explorer, and the additional window does not appear. Nice. This has demonstrated the basic functionality of an HTA exploit, but we'll need to try harder to turn this into an attack. Instead of using the run method to launch cmd.exe, we'll instead turn to the much more powerful and capable PowerShell framework. HTA attack in action. We'll use MSF Venom to turn our basic HTML application into an attack. relying on the HTA-PSH output format to create an HTA payload based on PowerShell. Once the complete reverse shell payload is generated, it's saved into the file evil.hta. Let's walk through the generated HTA file to better understand how everything works. One of the first things to note is that the variable names have been randomized in order to trick detection and antivirus software. PowerShell is executed by the run method of the Windows scripting host, along with 3 command line arguments. The first argument, -nop, is shorthand for no profile, which prevents PowerShell from loading the user profile, which might negatively impact the execution of our code. Next, our script uses -w hidden, shorthand for Windows style hidden, which avoids creating a window on the user's desktop. Finally, the extremely important -e flag, shorthand for encoded command, allows us to supply a base 64 encoded PowerShell script directly as a command line argument. We'll host this new HTA application on our Kali machine and launch a Netcat listener to test our attack. Then we'll emulate our victim by browsing to the malicious URL and accepting the 2 security warnings. If everything goes according to plan, we should be able to catch a reverse shell. Our malicious HTA file is executed, and launches our reverse shell. This attack vector allows us to compromise a Windows client through Internet Explorer without the presence of a specific software vulnerability. Since the link to the HTML application can be delivered via email, we can even compromise NATed internal clients. Exploiting Microsoft Office. When leveraging client-side vulnerabilities, it's important to use applications that are trusted by the victim in their everyday line of work. Unlike potentially suspicious-looking web links, Microsoft Office client-side attacks are more successful because it is difficult to differentiate malicious content from benign. In this section, we'll explore various client-side attack vectors that leverage Microsoft Office applications. Microsoft Word macro. The Microsoft Word macro may be one of the oldest and best known client-side software attack vectors. Microsoft Office applications like Word and Excel allow users to embed macros, a series of commands and instructions that are grouped together to programmatically accomplish a task. Organizations often use macros to manage dynamic content and link documents with external content. More interestingly, macros can be written from scratch in Visual Basic for Applications, or VBA, which is a fully functioning scripting language with full access to ActiveX objects and the Windows script host, similar to JavaScript in HTML applications. Creating a Word macro is as simple as choosing the View ribbon and selecting Macros. To begin, we enter a name for the macro. When we click Create, a simple macro framework will be inserted into our document. Let's examine our simple macro and discuss the fundamentals of Visual Basic for Applications. The main procedure used in our VBA macro begins with the sub keyword and ends with end sub. This essentially marks the body of our macro. At this point, our new macro, my macro, is simply an empty procedure and several lines beginning with an apostrophe, which are comments. To invoke the Windows scripting host through ActiveX, as we did earlier, we can use the createObject function, along with the wscript.shell run method, which we'll insert into our macro. Since Office macros are not executed automatically, we must make use of two predefined procedures, namely the auto-open procedure, which is executed when a new document is opened, and document open, which is executed when an already open document is reopened. Both of these procedures can call our custom procedure and run our code. We must save the containing document as either docm or the older doc format, which supports embedded macros but must avoid the docx format, which does not support them. When we reopen the document containing our macro, we'll be presented with a security warning, indicating that macros have been disabled. In order to run the macro, the default security setting of Microsoft Office dictates that we must click Enable Content. While macros can certainly be disabled in an attempt to guard against this attack, they are often enabled as they're commonly used in most environments. Once we click Enable Content, the macro will execute and a command prompt will open. If the user does not click Enable Content, the attack will fail. To overcome this, the victim must be unaware of the potential consequences or be sufficiently encouraged by the presentation of the document to click this button. As with the initial HTML application, command execution is a start, but a reverse shell would be much better. To that end, we'll once again turn to PowerShell and reuse the ability to execute our Metasploit shellcode using a base64 encoded string. To make this happen, we'll declare a variable of type string containing the PowerShell command we wish to execute. We'll add a line to reserve space for our string variable in our macro. We could embed base64 encoded PowerShell script as a single string, but VBA has a 255 character limit for literal strings. This restriction does not apply to strings stored in variables, so we can split the command into multiple lines and concatenate them. We'll use a simple Python script to split our command. We'll paste the PowerShell code from the HTA file we created earlier in this module, and save our script. Now we'll run our script and pipe the output into Xclip to send the split PowerShell command to our clipboard. Having split the base64 encoded string into smaller chunks, we can update and execute our exploit. But first, let's reestablish our Netcat listener. Then edit our macro again. Saving the Word document, closing it, and reopening it will automatically execute the macro. Notice that the macro security warning only reappears if the name of the document is changed. In our Netcat listener, we see that the macro works flawlessly and results in a working reverse shell. Excellent. Object linking and embedding. Another popular client-side attack against Microsoft Office abuses Dynamic Data Exchange, or DDE, to execute arbitrary applications from within Office documents. But this has been patched since December of 2017. However, we can still leverage OLE to abuse Microsoft Office's document embedding feature. Windows batch files are an older format, often replaced by more modern Windows native scripting languages such as VBScript and PowerShell. However, batch scripts are still fully functional, even on Windows 10, and can be used to execute applications. We'll create an initial proof of concept batch script, launch.bat, that launches cmd.exe. To insert this script into a document, we'll open Microsoft Word, create a new document, navigate to the Insert ribbon, and click the Object menu. From here, we'll choose the Create from File tab and select our newly created batch script. We can also change the appearance of the batch file within the Word document to make it look more benign. To do this, we'll recreate our .bat file link. This time, before we click OK, we simply check the Display as Icon checkbox, which brings up the menu box, allowing us to make changes. Even though this is an embedded batch file, Microsoft allows us to pick a different icon for it and enter a caption, which is what the victim will see, rather than the actual file name. We choose the icon for Microsoft Excel along with a name of readme.xls to fully mask the batch file in an attempt to lower the victim's suspicions. After accepting the menu options, the batch file is embedded in the Microsoft Word document. Next, the victim must be tricked into double-clicking it and accepting the security warning. As soon as the victim accepts the warning, cmd.exe is launched. Although this grants command execution, our ultimate goal, once again, is to leverage PowerShell, which is a more elegant solution. This time, the conversion is very simple, and we can simply change CMD to the previously used base64 encoded invocation of PowerShell. In order for our edited batch file to be executed, we must re-embed it into our document with a new object. Before executing our batch file, we once again establish our Netcat listener. After embedding the updated batch file, double-clicking our readme.doc file, and clicking through the resultant warning, we receive a working reverse shell in our waiting Netcat listener. Nice. Evading protected view. This Microsoft Word document is highly effective when served locally, but when served from the internet, say through an email or a downloaded link, we must bypass another layer of protection known as protected view. Essentially a sandbox feature for Microsoft Office, this protection disables all editing and modifications in the document and blocks the execution of macros or embedded objects. To simulate this, we'll copy the Microsoft Word document containing our embedded batch file to our Kali machine and host it from the Apache server. We'll do this with Netcat and listen for the file in our Kali terminal to transfer the file to our web root directory. Next, we'll download the file to our Windows client with Netcat and open it. At this point, protected view is engaged, and we cannot execute the batch file. While the victim may click Enable Editing and exit protected view, this is unlikely. Ideally, we would prefer to bypass protected view altogether, and one straightforward way to do this is to use another Office application. Like Microsoft Word, Microsoft Publisher allows embedded objects and ultimately code execution in exactly the same manner as Word and Excel, but will not enable protected view for internet-delivered documents. We could use the tactics we previously applied to Word to bypass these restrictions, but the downside is that Publisher is less frequently installed than Word or Excel. Still, if your fingerprinting detects an installation of Publisher, this may be a viable and better vector. Wrapping up. Client-side attack vectors are especially insidious as they exploit weaknesses in client software, such as a browser, as opposed to exploiting server software. This often involves some form of user interaction and deception in order for the client software to execute malicious code. These attack vectors are particularly appealing for an attacker because they do not require direct or routable access to the victim's machine. In this module, we described some of the factors that are important to consider in this type of attack and walked through exploitation scenarios involving both malicious HTML applications and Microsoft Word documents.
We hope you enjoyed the video and found value in the content. We value your feedback. If you have any questions or suggestions, feel free to post them in the comments section or contact us directly via our social platforms. Thanks for watching.